So good morning, everyone.
Morning.
We are Team Align, and this is our spring validation demonstration. We'd like to begin by thanking our sponsor, Pix Moving, represented by Nancy and Chase on this call, for the support in these trying times, and to Professor Alex from Nagoya University, who has been our technical mentor throughout our development. We also want to thank Professor Dimi and Professor John for their constant support and feedback. We will now begin with the demonstration, which consists of two separate simulations. We have prepared slides which detail the steps we will be following for each test, and Uma will be sharing the link for the same in the chat for your reference. Since tests 1 and 3 use the same simulation, we will be performing them first. So the aim of the first test is to have the chassis navigate from a designated starting area to the payload handling zone entry point. We've broken this down into 7 parts. First, we've launched the Gazebo world simulation. You can see the chassis on the bottom and the pod on the top left. We've also loaded the Gazebo world point cloud map into Avis. Next, we'll be starting the Autoware localization and planning nodes. The red circles that you can see on the map are the point clouds that will be used by the localizer. And you'll see a yellow box appear on the screen, which will represent the payload handling zone, which has been obtained from the prior estimate of the pod available to the system. Now we will ask the chassis to plan a path to the pod. The green strip is this planned path. Next, the chassis will start traversing this path. The white line is the instantaneous pure pursuit trajectory, the tracker that we're using for path following. Now, as the chassis moves, we'll be placing obstacles in its path. And we will see that the chassis stops well in time. And once the obstacle is removed, it continues its motion. This is a part of test 3, and we're doing it right now in order to save time. Now, the chassis will continue moving towards the payload handling zone starting point. When it is within 2 meters of the starting point, it will indicate that the zone has been reached.
Yeah, so the chassis is nearing the 2-meter mark and it starts predicting that it is able to, it's in the proximity of the PH3 entry point. It then comes to a halt and it will now identify the pod using the AprilTags on the pod.
Yeah, so this is the view that the camera on the chassis sees. And we see that the predicted estimate of the pod by the chassis is around 39.5 in X and 38.9 in Y. When we go to the actual simulation and compare this with the actual ground truth, so so when we compare it with the ground truth, we see that they're very close by and the prediction is quite accurate. This ends test 1.
Yeah, so let's move on to test 3. This test consists of 5 parts. The first one of which is manually crashing the obstacle avoidance node. And the expected outcome for this is that the persistence check that occurs in the health monitoring system will detect the crash node and send an error message. Create an error log basically. Yeah, here you can see that the node has been killed and this particular error message is being published that the service call failed. The second test, for the second test, we'll manually stop publishing to the NDT post topic, and the expected outcome is that the persistence check in the HMS will detect that the node has crashed. So here you can see that NDT matching is stopped, which means that there's nothing being published to the NDT post topic, and then you can see that data is not being received in the error message. For the next test, we'll restart this node so that NDT pose is being published, but after introducing some misalignment. And the expected outcome is that the sanity check should detect that the wrong pose information is being published.
And
for our next test, we will publish incorrect LIDAR data to the scan topic, and the sanity check in the expected outcome is that the sanity check in the HMS detects that incorrect data is being published. So this data is actually consists of negative values, and here you can see that the error log is being published that the HMS has received invalid laser scan data, and it's also instructing the vehicle to come to a halt in this case. And for the final test and for the final part of the third test, we'll try to cause collision using teleop, that is, we'll control the car manually, and the obstacle detection node should prevent collision from occurring via the HMS and also publish an error log. You can see that the obstacle has been detected, the error log is being published, and the vehicle has been instructed to come to a halt. So I'll be sharing my screen to demonstrate the obstacle detection using the YOLO network as well as Euclidean clustering on the LiDAR. We are doing this separately from the test because these tasks are computationally intensive and do not work well with Zoom. So here we have the YOLO network, and once I remove the obstacle, I'm sorry, are you able to see my screen?
Yes.
Okay. So you can see that it detects obstacles like fire hydrants, cars, stop signs, and persons, which we would usually find on a campus environment. And it also shows that the car is being detected with a very high confidence. And there are some false positives sometimes, but I think it's better than having like false negatives. And then you can also see that it detects these vehicles which do not resemble either a bike or a car, but something else. And both the stop signs here are detected. So here we have the Euclidean clustering, which will detect obstacles. And you can see that right now no obstacle is being detected. And we'll start the object detection node. It's not publishing anything again because this obstacle isn't being detected yet. As it comes closer, it will start being detected. And you can now see that these colored points show that the cluster has been detected, and here information has started publishing. This is the X and Y location with respect to the Velodyne LiDAR. That's on the center of the vehicle, and the error here is the error between our estimated position and the ground truth position. So once again, when I bring the obstacle closer, it will start publishing it, and the error between our estimate and the ground truth estimate is 5 centimeters, which is what our requirements were. So you can see that, and yeah. And then coming just a small demo of the LiDAR detection while the vehicle is moving. So you can see that this is not with respect to the blue rays, this is to the LiDAR in the center of the vehicle. So here you can see that it will start detecting the Husky over here and this Robonaut over here. So yeah, this is the Husky, this is the Robonaut on the right. And moving forward, it will start, both the cars are being detected as clusters. I'll put an obstacle over here now. So it's able to detect this unit cylinder that is being kept. And finally, it's able to detect that this fire truck is over here and it will stop. So that is the end of test 2, and we'll move on to test 3 now.
So for the next pair of tests, we're actually going to be switching out our simulations. And the main reason for that is because we wanted more fine-grained control of the PID parameters for the purpose of approach navigation. So we decided to switch out the simulation to have one with just the chassis and the pod. So our first set of tests would be a set of 6 sub-tests, and this would be in a different simulation. So we'll first launch that with the pod and the vehicle with the AprilTags loader on the pod. Yeah, and this is what that would look like. And the first set of things to do would be to launch the LIDAR-based localization and planning nodes and load the pod location prior estimate. And these will be visible in RViz. So this is the image from the camera. And then in RViz, we can see that the yellow rectangle corresponds to the prior estimate of the pod location. And the green rectangle, which is almost perfectly overlaid, is the estimated location based on the 2D LiDAR localization. So it says there that the goal orientation of the pod is being predicted to 3.9904 in X and 0.002 or 3 in Y. And the actual location is 4 and 0 in the simulation. So that's why the rectangles are almost perfectly aligned. And then we've generated a set of waypoints for approach navigation. So those are being visible in RViz as the green arrows shown in the figure. And then the execution of this approach navigation will be done with pure pursuit and PD velocity control. And then we'll see that the chassis will follow these waypoints and align itself under the pod. And then once this alignment is completed, we're going to be performing pose verification using the laser scan data. So it will finish this docking procedure. It'll say that it's finished, and then it'll run this pose verification. So now it's checking the pose error, and then it obtains a pose error of 1.7 centimeters. And now we'll be doing a similar docking procedure, but oh yeah, so we can also visually verify that the docking is performed more or less perfectly. So now we'll just be performing the same procedure again, but then we'll be introducing a slight misalignment, both in the XY position as well as in the orientation. So this is a slight orientation error and position error.
And for that first test, what was the error? It was like 2 centimeters?
1.718 centimeters, okay. I think.
1.7.
Yeah. Yeah, so now this is the same docking procedure, but with that slight misalignment being introduced. And then it does the same following of those waypoints and then does the pose verification. Sachit, can you bring up that terminal?
Yeah. So Rohan, for this one, the correction was done outside the pod?
Yeah, the correction was done outside the pod. So in this case, there's this another factor we added, which we skipped last time because the errors seem too high in that. So this factor actually corresponds to the error measured through the 3D LiDAR scan data.
Mm-hmm.
But the problem with this is the current simulation, even if you see this for a while, the points will start disappearing from the Velodyne data. So because it's not actually, it runs on my GPU and sometimes it just skips out a lot of points and becomes nans. That's one of the reasons why even in our HMS, it was switching to warning about the 3D LiDAR data.
Mm-hmm.
So this error we usually are right now ignoring, but this is basically the center of the pod predicted from the point cloud data.
The 3D LiDAR, yeah.
Okay.
And now we move on to the final set of tests.
So our final, last but not the least, our final test is a retracing. So again, we will begin with the docking procedure.
Can you guys tell us, I mean, I know retracing is in the document, but what do you mean by retracing operation?
So basically when the error is too high, the chassis should just go back to the starting position. That's what.
Yeah.
So now we will manually introduce a misalignment to simulate any real world uncertainties that may arise.
Okay.
And as you can see, and you can see the error is pretty high. So the bot begins to retrace its path to the start of the PHC. It will begin to dock again.
That's weird, yeah.
And now the error will be calculated. you can see, it's well within our requirements, and that's pretty much it. We are open to questions.